molar solubility, which just tells us how many moles we can dissolve in a liter. And for some things, you can't dissolve that much. The molar solubility of silver chloride is pretty small. Other things like sodium chloride, you can dissolve quite a lot. A lot of moles. HCl, same thing, dissolve a lot of moles. But what is a lot of moles? A lot of moles would be like 18 molar. That would be high. Or something like pure water. Do you know what the molarity of pure water is? This is not solubility, but this is just molarity. Pure water, if you have a liter of pure water, how much does it weigh? It weighs 1,000 grams, 18 grams per mole, so 55.5 moles. So pure water, you can fit 55.5 moles of pure water in a liter. And so there's that one particular homework problem with 110 molar. And sometimes you lose sight of the numbers, but it's nice to have some reference points for numbers, because if you hear somebody say 110 molar solution, does it sound funny to you? Yeah. Okay, then that's good. Then you have a sense of it. But sometimes when you see it in scientific notation, it doesn't sound so funny, like 1.1 times 10 squared molar. And it doesn't sound so funny. Okay, that was the first part. The second part, it looks like everybody got 120 drops. Using KSPF. If you didn't get 120 drops, like we've just done some simple calculation there, so you want to check that. Okay. There's a huge difference if you dissolve in ammonia. Why? Why was there such a huge difference between dissolving in ammonia versus dissolving in water? And so that's one of the things in this particular chapter. We look at KF, and so what's one of the things that we use KF for? KF is to form complexes. And so a while back ago, I talked about aqua regia. And aqua regia is used to dissolve gold. Gold is very difficult to dissolve. We can try to dissolve gold under standard conditions, maybe by oxidizing nitric acid. Okay, thanks. And so if we oxidize it using nitric acid, then what we'd like to form is gold 3 plus. And whatever else. In fact, what we would do is we just do this using the chart method. And so we have gold, solid, H plus, nitrate, and water. And so we figure out the strongest reducing agent. The strongest reducing agent will be, in this case, gold. The strongest oxidizing agent will be a combination of nitrate and H plus. Reducing agent, oxidizing agent. Gold can get oxidized to gold 1 or gold 3. In this case, we take it to gold 3 plus 3 electrons. Here, the nitrate, we just copy out the chart. It's nitrate plus 4H plus. Actually, what we could do is we could figure it out. 3, 5. Nitrogen goes from plus nitrogen plus 5 here to plus 2. So plus 5 to plus 2 would be plus 3 electrons. This is going to form NO gas plus 2H2O. So we combine these two half reactions, and we'll end up with gold 3 plus. And That's what we want. But the problem with this is there's no driving force. So we have gold solid plus nitrate plus 4H plus yields gold 3 plus NO gas plus 2H2O liquid. Two out of the, actually 3 out of the 4 nitrates, because if we have 4H pluses, we have 4HNO3s. 3 of those are spectators. And those 3 nitrates that are spectators just cancel out, so I didn't show them here. We could have put them here, this is a form of gold 3 nitrate. And 3 nitrates balancing out the charge of the gold 3. Okay, the problem with this reaction is we do this, and what we get is this. We get that this reducing agent versus this reducing agent. We're going from a weaker reducing agent, gold, to a stronger reducing agent. And then we're going from a weaker oxidizer to a stronger oxidizer. We would have to use the chart I gave you. It doesn't have gold on there. We have to use appendix D. Appendix D has gold 3. Gold 3 is a very powerful oxidizer. And so there's no driving force for this. If we calculate the delta G for this, we would see that delta G is greater than 0, which means it's non-spontaneous. Okay, this is delta G standard conditions at 298 Kelvin. And just because we have delta G under standard conditions at 298 Kelvin doesn't mean we should just take that and then just forget about trying this. What we can try to do, the first thing we can try to do is maybe try to do what? To make this go. We could try heating it up, or maybe even cooling it down, depending on how temperature impacts delta G. And by heating it up or cooling it down, we have to look at the entropy. If the entropy is increasing, then we want to heat it up, because heating it up will help the entropy term. If the entropy is decreasing, we want to cool it down, because that will minimize the negative entropy term, which we don't want. In this case, what does it look like the entropy is doing here? Yeah, the entropy is increasing. So maybe hot nitric acid would help this, right? Because when we look at our delta G is equal to delta H minus T delta S. All right. I don't know if we have data for appendix D, but we could calculate it and then see, is there a temperature at which this will switch from non-spontaneous to spontaneous? But there's a major problem here, and in theory, we can just keep increasing temperature, but it's like the numbers, there's going to be a theoretical limit, and then there's going to be a practical limit about what you can do. And so let's say I calculate the temperature, but that temperature is going to be, regulated to a maximum temperature of what? I can't just keep increasing the temperature. I'm going to be limited to a temperature of what? Because what's one other component of this mixture? One other component of this mixture is water. And so I can only go up to about 100 degrees C. And if I try to go beyond that, I either got to do this in a pressure cooker, which is okay. I could do this in a pressure cooker, but the pressure cooker, we can put it in a pressure cooker and maybe increase the boiling point of the water, maybe to, we could calculate it. But it doesn't increase all that much. We'd have to have pretty extreme pressures. You could have pretty extreme pressures, like in geology, you can have all these other types of reactions occur. When I was into geology, where did some of these minerals form. These minerals form like in a pressure cooker under the earth. So if you're looking for certain types of minerals, you look for those types of situations. Like I know some of my classmates are really interested in finding like diamond deposits and gold deposits and this kind of stuff. So they're really interested in what types of environments favor the production does. But and so they're always out looking. But anyway, getting back to this, and in fact, one of my students is searching for gold up in the mountains here. I mean, he brought some gold in. He showed me. He collected maybe over an ounce of gold, just from panning for gold. I don't know how many hours he spent doing that, but it's pretty impressive. Anyway, gold's very valuable because it's really hard to oxidize this stuff. In fact, that's why they use gold in electrical contacts, because it's so resistant to oxidation. Whereas copper, copper, pretty soon the contacts go bad. You lose that electrical connection. Electrons have difficulty flowing. There's a lot of what we call resistance. And anyway, this stuff is hard to oxidize, so delta G is greater. So we could try changing the temperature. Like this one looks like higher temperature, but we're limited. And you could try doing a pressure cooker. And so, yeah, increased temperature will help. So hot nitric acid, I'd like to use that. What else could we do? Do that. So if we change the temperature, we can still do that under standard conditions. We could also do a combination of things. If we change the temperature under standard conditions, then all we do is look at delta G naught, how it changes, with temperature. And so for this, we're going to just say, well, we're going to say that this is about equal to delta H naught at what? 298 minus T delta S naught at 298. Now, of course, if the phases change, like H2O goes from liquid to gas, then it's not going to work. Delta H is not the same for steam as it is for liquid water. Delta H changes significantly depending on the state, and so states are extremely important. So this only works for a certain range. It doesn't work for all temperatures. But you have to limit it within a certain range where these things are what they are. And so you can't use it blindly. So here for us, we want to increase the temperature. We can do the calculations. We just look up the data in Appendix D. Pretty sure gold is in there. We can figure it out. What else could we do? Well, temperature is one, and
do like a Le Chatelier shift.
Yeah, we could do like a Le Chatelier shift, so we can try to get rid of the gas maybe, and now try to get rid of the gas and then shift it to the right. Try that. That would be what we call non-standard conditions, because under standard this reaction, and the reason standard conditions are really, nobody ever really does reactions under standard conditions. It doesn't quite make sense. So if I were to do this reaction, there's no way I would do it under standard conditions. The reason why is under standard conditions, the solutions have to be 1 molar and the gases have to be 1 atmosphere or 1 bar. So in order to do this under standard conditions, I'd have to have 1 molar here, and I'd have to be bubbling NO, gas, at 1 bar in the products. Do you want to be bubbling NO gas? I mean, why bother? You're trying to produce this, or, and in fact, if you're bubbling NO gas, it pushes the reaction backwards, but this is the constraint we have under standard conditions. Everything, reactants and products, have to be under standard conditions. And so this means that whenever you do a reaction under standard conditions, you have to have both reactants and products all at one. And that gives you a K of 1. In fact, I would do this with no product in there. I don't want to add product because not only do I have to have NO at bar, I'd also have to have gold 3 at 1 molar. Does it make sense to, you're trying to form this stuff, does it make sense to put it in there to begin with it? And so under standard conditions is weird, but it makes sense why it's like that. If it's not like that, then we can't reverse the reactions. And so all the reactions that we do are not reversible in the sense that we're going to have to, if we reverse it, we're going to have to change everything, you know? And so if we do things under standard conditions, it means that we have a lot less. It's going to be more compact as far as the data goes, and then we can adjust it, you know? So if we try it under standard conditions, yeah. But the thing to do here is to kind of try to shift it to the left. So if we do this under non-standard conditions, then it would be delta G under non-standard conditions is equal to delta G under standard conditions. And then the correction, and the correction is going to be this RT ln Q. So what we want to do is we want to make Q small or we want to make Q big in order to try to push this to the right. If we make Q big, then ln Q is going to be bigger, and then RT, and that's going to make this more positive. Do we want to make delta G more positive or delta G more negative? More negative. So we want to make this small, extremely small. Extremely small means very little product, mainly reactant. If we make this big, then that means mostly product and very little reactant. And so what we can also do is this. The more concentrated we make the reactant, the better, and the less concentrated we make the product, the better, because that's going to give us a bigger Q. And so something like this, we would want to make this as concentrated as possible. What's the most concentrated you can make the nitric acid? When you buy it, the most concentrated you can get the nitric acid commercially is not 12. Sulfuric acid we can get at 12 molar in a thick syrup, or 18 molar. Nitric acid we could get at about 16 molar. That's most. And so what we use is we use hot concentrated nitric acid. Hot concentrated nitric acid might get this to go, you know. So maybe under standard conditions it doesn't go, but we don't give up there because obviously we can change the temperature under standard conditions, and if that doesn't work, then we can just get rid of standard conditions altogether and go non-standard conditions. And we can go non-standard conditions at different temperatures here. But there's a problem here, that is this delta G under standard conditions, we usually calculate that at what temperature? At 298. Now, if we're not at 298, then we don't know what that delta G is, because sometimes, unless we do this. So this is another, rather than having this delta G, which is typically at 298, we'll substitute what for that? Delta H. Delta H, we're going to substitute delta H at 298, assuming that it doesn't change much, minus T delta S at 298, plus RT, ln Q. Okay, this might be positive. If delta G under non-standard conditions is positive, then it's not going to work, right? And so what we try to do is we try to get that to change to negative. And in order to go from positive to negative, it's going to transition, through zero. So we set it to 0 in order to figure out at what conditions it transitions to. And those conditions could be a combination of temperature and non-standard conditions to try to get it to go. But let's say it still doesn't quite work. I tried, about the most concentrated I can get is about 16 molar. I try to heat it up, but I can't heat it up to infinitely hot temperatures. And so what else can I do? Well, I don't quite give up there. If I want to get the gold to dissolve, I could try to not remove the NO. Yeah. Yeah, I could try to get rid of the gold 3. How can I get rid of the gold 3? Probably the easiest way of getting rid of the gold 3 is by complexing it, right? If we complex it, then that would be probably the best thing to do. So if I can get rid of the gold by complexing it with what? Yeah, whatever in the chart says. So let's look at the potential complexing agents for gold 3 here from the chart in our book. Appendix D. But what do you think might work? Well, what might work are, ligands. Do you guys recall what the best Lewis bases ligands are? Carbon, yeah, right. Carbon donor, nitrogen donor, oxygen donor. And so what were some typical carbon donors that these were good Lewis bases for metal cations? I gave 2 examples of carbon donors. You remember those? It's not just any carbon because it's a very special carbon. Very special carbon that has a very unique formal charge on the carbon atom. What was that unique formal charge on the carbon atom? Yeah. It was negative what? -1. And so give me an example of 2 things where carbon has a -1 formal charge. Cyanide and these are 2 things you don't want to ingest because your hemoglobin in the blood has iron 2 in the center of it. So we have iron 2 in the center of your heme. This is called the heme group here. Heme is just one giant ligand.
Carbon monoxide?
Yeah, and carbon monoxide. Those are excellent ligands for metal cations. And so rather than oxygen is not that great of a ligand. The oxygen does have lone pair here, but it doesn't form a very strong bond here when oxygen attaches here, which is good because you don't want too strong of a bond. Otherwise, the oxygen can't be used if it's too strongly bound to it. But something like cyanide or carbon monoxide will form a very strong bond to the iron 2. And then if there's carbon monoxide, there's a competition, oxygen versus carbon monoxide wins. Oxygen versus cyanide wins. So carbon monoxide is used as a ligand for these, and there are what we call carbonyl complexes. And some of these are very stable. One of these in particular, let's look at carbonyl complexes. Let's see what this says. This is from Wikipedia. You see a whole bunch of different metal carbonyl complexes. Carbonyl or carbon monoxide is an excellent ligand here. And we can just read this short thing. Metal carbonyls are coordination complexes that transition metals with carbon monoxide ligands. Metal carbonyls are useful in organic synthesis and as catalysts or catalyst precursors in homogeneous catalysts such as hydroformylation or record chemistry. Something like that. And so they're not all bad. Cyanide is another one, but carbon monoxide is a gas. So I probably, if I'm just guessing as to what might work well, I would guess maybe carbon monoxide would work pretty well, or cyanide. Cyanide is an excellent ligand, and it's been used a lot. So it's used in gold mining, cyanide. So the cyanide pits. What are the dangers of using cyanide? I guess Mexico, obviously there's a lot of these gold pits they're trying to. I think I talk about near the 14 freeway, Mojave. Yeah, all right. United States, there's 52,000 gallons of cyanide solution poisoned the aquifer that supplies fresh drinking water to town absorbent. That's 1982. That's pretty tragic. The accident was discovered when an employee of the mine noticed the smell of cyanide in his tap water at home. Yeah, that's pretty bad. And so obviously, if you're going to use cyanide, you need to be extra careful using cyanide and make sure nothing like this can happen. And so this is why they're taking extra precautions with some of these old gold mining pits. They're trying to leach the remaining gold out of there using cyanide. But we don't want to use cyanide for this because cyanide is, hazardous. So we think of other ligands. So this is a carbon donor. This is if we don't have the table. We look for patterns, right? We look for patterns if we don't have the table. If we have the table, then we just use the table as is. And normally when we're trying to learn stuff, we just use the table as is and then look for patterns because those patterns will come up as we're using it. And so if we come back to the table, let's take a look at the table complexes and see what types of ligands. The oxalate's an excellent ligand, for sure. Oxalate's good. But unfortunately, this is what often happens. What often happens is we look and do you see any gold here? No, silver. And so we might try to use things like silver, things that might work okay with silver might work okay with gold, perhaps. So you could try that. Silver and gold are in the same family, right? And so we try to do something like this to try to figure things out. And so it looks like cyanide is an excellent ligand. It looks like cyanide's the best ligand out of all these for silver. So cyanide for sure, but we don't want to touch cyanide. EDTA, ethylene diamine tetraacetato, ethylene diamine ammonia. These are thiocyanate, thiosulfate. Sulfur likes heavy metals like silver, gold, lead. Sulfur is actually good for binding to those. Okay, so we don't see that there. We could look at gold complexes. And see what types of ligands. Gold 3 complex and an overview of the kinetics. Kinetics plays an important role, like, in certain things. So, for example, if we go back to this heme here, this would be what we call a labile complex. Labile complex means the oxygen can come off easily and bind easily, so it's labile. Whereas an inert complex has very slow kinetics. Inert just means it's very unreactive. It takes a long time to react. So a cyanyl complex of iron here or carbonyl complex of iron here would be an inert complex, not very reactive for that. And so that's kinetics here. And so an overview. Recent advances of gold compounds in anti-cancer immunity. It's interesting. It's in 2020. So, etc. So we look. It turns out one of the complexes, and this is a very inexpensive ligand, and it's not very toxic, is chloride. And it turns out that people figured this out. Well, does chloride work? Well, there are two ways you can do this. You can do this theoretically. That is, you can try to do some quantum mechanics and figure out if it's going to be successful or not. Or you can just do it empirically. Empirically, just mix it together and see what happens. Try lots of different ligands. And it turns out that chloride's okay. And so if we take 4 chloride, that's going to make this complex. This complex is the tetrachloroaurate 3 ion here. And this is favorable. Chloride turns out to be a decent ligand. And we see that chloride, I don't think chloride's a very good Lewis space. And I wouldn't, because halogens, remember the halides were the worst. So when we look at this, we might get an indication that chloride might be okay, because we have the tetrachlorocadmiate here. And then we have the trichlorocuprate 1 here. And then we have the tetrachloromethorate here. The tetrachloroplatinate here. Trichloroplumbate here. These are all heavy metals here. And it looks like chloros. And so this is a pattern that we see. And this pattern, maybe we could guess that it might work okay for gold, and then it does. It's a pretty good ligand for gold. And so this is how we use this. I mean, this is a lot of data, this data table. A lot of people just look up the data, but what we do is we try to look for patterns in that data so that we can see, try to make predictions based on that. Because, if we're going to start mixing things, well, I don't know how they figured aqua regia out, but somebody figured it out. Aqua regia is a mixture of nitric acid and hydrochloric acid. And this is used in salt gold. And so let's take a quick look. And it's mixed in a 1-to-3 ratio, aqua regia. And I saw this really interesting YouTube video where they were trying to recover gold from old electronics. Old electronics will have gold contacts. Those gold contacts are and very, very thin plating of gold on there. They aren't solid gold. And so what they did was they used aqua regia to recover it. And I don't know about like the environmental, what if they
lot of these YouTube, they don't have to conform to the strict standards that like, businesses or commercial operations would have to. But, well, I guess you call it gold recycling or gold recovery in electronics. Have you seen that? The amount of gold is surprising. This person ended up with, well, I don't know. I don't think this is the one, but okay.
You don't need a waffle maker. Yes, you do.
No, I don't know these guys.
Oh, it's not okay. It's installed. Thanks, Google. Pick it up, flip it over. You got it. Go have it now. Get it near you. Shop with Google.
You always wear suits and ties? Of course.
All right. Forget it. But you could see that some of these people cover significant quantities of gold here. And there's one person, and it's 2.8 grams. 2.8 grams of gold is worth how much? $1. So it's a lot. Yeah. I mean, an ounce of gold is an ounce? Yeah, I mean, how many grams is how many ounces is 2.8 grams? That's a lot. That's a lot.
There's only 3 seconds left.
Yeah, there's only 3 seconds. We will wait.
All right. Well, I don't know if there's another ad after this one. All right.
Thank you.
You want to see the gold result?
Well, this isn't the one I watched. I gotta find out a minute. It looks like they already leached the gold out of there. The other one was actually recovering it from the electronics, so I'd have to find it. Yeah, since it doesn't pop up on my thing. But that's aqua regia.
Really that color?
Yeah.
No.
You know what that brown gas is? That's nitrogen dioxide. The NO gas is colorless, and that gets converted into NO2. NO2 is characteristic of nitrates burning. If you just added nitric acid alone, nothing happens. You have to have the chloride in there. Let's speed this up. So what they're trying to do is they're trying to recrystallize it. They're trying to recrystallize the gold to get rid of the impurities. And so what you do in recrystallization, you dissolve it and then you try to precipitate it out pure, and leave the impurities or filter out the impurities or get rid of the impurities in some way or another. So we'll speed it up here. But there are lots of videos on there. Okay, so then they were able to recrystallize it as precipitate here, get rid of the impurities. Although it doesn't look so pure, does it?
No.
Looks like dirt. And then they melted it. Okay, that looks more like gold. I don't know what the purity is there. But yeah, I think this is one of these here where they just take it from the circuit board. And actually, that's a lot of gold there. right, so what we're doing is we're going to combine these because here delta G is greater than 0, and here delta G is less than 0. When we have complex formations, remember the K is very large for these. KFs are very large. If KFs are very large, what does that tell us about the delta G? The delta G is equal to, under standard conditions, so delta G under standard conditions is equal to minus RT ln of K. And so if K is very large, then ln of K is big, and that makes this more negative. And that makes delta G more negative. And so things with a large K are going to be negative. And all we're going to do is we're going to combine these two equations. If we combine these two equations, then we'll get what aqua regia was. So it's going to be gold, solid. Okay, so we'll add up everything on the left. So, and then what cancels out? Gold 3 cancels, and that's it. And so we'll have gold solid plus nitrate plus 4H plus 4 chlorides produces this tetrachloroborate complex plus NO gas plus 2 H2O liquid. Now the NO gas gets oxidized in air. So this, in fact, maybe we should go straight to NO2, but in air, NO gets oxidized to NO2 by reaction with those two here. And this is brown. This gas is colorless here. Now, when we do the delta G for the net reaction, the delta G for the net reaction is just delta G for step 1 plus delta G for step 2. So this is just equal to delta G1 plus delta G2. Yeah. And if we can keep this under 0, that is, if we keep this negative, then this goes. In fact, that's what happens in this particular case. And so this is an example of complexing to take advantage of the Chaudelet's principle to shift this reaction to the right. What we did in chapter 18 is we look at KSP. KSP, shifting it to the right, just means dissolving it. And so we just try to dissolve things using KSPF. But this is the same type of deal here, where we're just trying to shift it to the right using complexing. So this is one of the things that we do for this. And when we do complexing of this, the free gold ion concentration is very small because most of the gold is here. The combined method works here. The combined method works because the first one is small. You know, K is very small. Delta G is kind of big. You know, K is small. It's mostly reactant. Delta G is big because it's mostly reactant. It's favored in the reverse direction. And so that keeps the gold 3 concentration very small. And whatever gold 3 concentration is generated is quickly vacuumed up or mopped up or reacted with chloride here, the chloroligand. And so we don't expect much gold 3. What's missing in this is gold 3. Where's the free gold ion? Well, the free gold ion we can assume is very small. Otherwise, we have to do this simultaneous. If that's not the case, sometimes we just have to do that. So here, this is the this happens in biology quite a lot. Coupled reactions. You know, you're like, for example, biologists have an interesting way of showing coupled reactions. Just do that. So if we look at ADP and ATP, these are energy molecules. ATP is the energy molecule for the cell. And so how do you make ATP? ATP made is, this is unfavorable. And so here, delta G is greater than 0. But what you can do is you can couple this reaction with something else. If you couple this reaction with, we have a delta G, which is less than 0. And so at the same time we're doing this here with a coupled, this is called a coupled reaction, which is favorable, then the overall, the net process can be delta G less than 0. So you can do that. So they show these coupled reactions like this where they couple it together in this way, but they don't combine like we did. But we combine so we can do some calculations. We're just coupling to show that they can go spontaneous. So the typical KF calculation will be things like how much free gold is there. Was that a decent assumption? So we can calculate how much free gold is in there. You know, there are some variations of this, like when we're looking at the decoupled reactions. The only time we would like do it like independently, separately, is when we're asked questions like this. You know, will a precipitate form? Will a precipitate form? We might try to do it decoupled rather than coupled. So let's say if I'm looking at silver chloride solid, there's the silver ion plus chloride, then will precipitate form? Will precipitate form? That's a QSP question. You know, QSP is greater than KSP, a precipitate form. And so a case where I might do this decoupled would be something like this. You know, will a precipitate form if I have, say, 0.1 molar silver ions here in the solution? Will a precipitate form if I have 0.1 molar silver ion in, let's say, 1.0 molar ammonia? And let's dump in some chloride in there. Let's put in and 1.0 molar chloride. There's going to be some sodium. Let's put some sodium in there, 1.0 molar sodium. And so the question might be, will a precipitate form in 1 molar sodium chloride in a solution that's 1 molar in sodium chloride and 1 molar in ammonia? Will a precipitate form? And so in a question like this, if this wasn't present, for sure precipitate is going to form, because when I calculate QSP is going to be 0.1 times 1, which would be 0.1. And KSP is like 10 to the minus 10. And so for sure precipitate is going to form. But in this case, will precipitate form? And so here we might try to do it not coupled or combined. What we might try to do is separate. And so the separate would be to calculate the free silver ion concentration in the presence of this ammonia. And so the free silver ion concentration in the presence of that ammonia can be calculated like this. This would form the diamine complex here, plus like this. And then what I can do is I can calculate the free silver ion concentration here, starting off with initial 0.1 and 1.0 molar. I want to reset this because KF is so huge. I'd reset this. And then eventually I'll calculate the free silver ion concentration at equilibrium. Once I know the free silver ion concentration at equilibrium, which is going to be very small, I'll plug it back into QSP and see, does the QSP exceed the KSP, and see if it precipitates or not. And so we don't, it's not automatic that we couple everything. There are some scenarios where we might just leave it separate, not do a KSPF. If we did a KSPF, we could do the same thing, but it's a little bit more complicated. I mean, we could get the answer, but we just have to think it some more because the KSPF, actually, we could do that as well. And so, in the book, we'll do it this way for certain problems. Okay, so that's how you use the KF. We use KF for different things. All right, were there any other questions?
For complete precipitation, is it 99.9 or 99.99%?
What did I say in class? 99.99 or 99.9?
99.9, but I think in the homework you said 99. Or in one overview you said 99.9.
I said that I was sleepy. I remember saying that because I was sleepy. It's 99.9.
Is it 99.9? Okay. 99.9, 99.99. Not a big difference. Well, I guess maybe there is.
I mean,
3.9.
asking us a question, that's like,
Yeah.
is this complete?
Yeah, let's just use 99.9.
Okay, thank you.
Complete. $99.9. Any other questions?
Could we go over a problem that was like, in the ice table, you multiply the concentrations by 99?
Oh, okay. The one that's asking about multiplied it.
I'm trying to find a problem.
Is how many drops required to precipitate 99.9% of the silver?
Oh, okay.
And
Does it have complete precipitation, which would be 99.9%?
how many drops are required to do 99.9%
Okay.
to precipitate?
In that chapter and in this chapter, chapter 13, I haven't gotten to the problem yet, but also in this chapter, we can manipulate how much reaction occurs. You know, not only do we want, let's say I wanted the gold to dissolve, so what kinds of things can I get or can I do to get the gold to dissolve? But I could be even more specific. Let's say I don't want all the gold to dissolve. Let's say I just want 50% of the gold to dissolve. Then what do I have to do to get just 50% of the gold to dissolve rather than all of it? And so in that case, what we do is we set up the ice table so that only 50 or half of it reacts, and then figure out what conditions make only half of it react. And so that way we can control the amount of reaction that occurs. Let's say, you know, it's either, a lot of people think, okay, I either want 100% or I want 0%. But no, even if you want 100%, it's still like, what, 99.9% or whatever, you know, you're doing. And so, so that commonly has you do this in the ice table. This is something that we don't commonly do in an ice table. Let's say, I'm looking at the combined method here. And, you know, I don't want to waste chemicals. You know, let's say I know just how much I want to dissolve and for a particular application or something like that. And so there are different things that we do for this. Here, we set a target, you know, molarity here, and then we figure out how to get to that target molarity here. And so it depends on how much I have, and it depends on how complicated I want to get. The easiest thing to do is if I don't have to deal with solution dilution. If I don't have to deal with solution dilution, then I don't have multiple equations and multiple unknowns to deal with. And so if I could add, let's say, ammonia gas, rather than adding drops of aqueous ammonia, it'd be a lot easier. And then I have a fixed quantity, so I could have a fixed molarity here. But let's take a look at some examples of this. Was that in the homework, you said? I multiplied by 99.9?
It was in class that you said it was a challenge problem and you probably wanted to ask this.
Of how many drops of ammonia would it take to dissolve?
And it ended up being like 1.1 billion drops, something like that. Actual precipitation.
Okay. In this chapter, I didn't ask you about partial reaction or something like that. In chapter 13, there are some questions about partial reaction. But they're a bit simpler. So if we look at this reaction, nitrogen plus hydrogen yields ammonia. And then we'll balance this equation out. So we have, let's go with 3 of these to make 2 of these here. This is gas. Gas. So sometimes what we do is we try to figure out, because sometimes taking it to, let's say, 99.9% reaction is potentially a waste of energy and a waste of time. Maybe 80% is adequate, for the reaction, because 80%, to get that extra, let's say, extra 10% or extra 19% or extra 19.9% reaction requires to go too extreme. And, we change this. And so this is a combination of things. So, like when I was talking about boiling water, we could boil water at room temperature, but boiling water at room temperature requires a huge vacuum. The vacuum, it's going to come out to 0.03 bar, or around 0.03 atmospheres. And that requires a very strong vacuum pump to boil water. And so what we do is we do this. If we want to get rid of the water, we use maybe not as powerful of a vacuum pump, much cheaper vacuum pump, and then just increase the temperature. Maybe we don't want to bring the temperature all the way to 100 degrees C, but maybe we could boil the water at like 50 degrees C. At 50 degrees C, it's much cheaper, but we'll need a little bit of vacuum, but we could use a cheap vacuum pump for that. Well, those already exist. Those are called vacuum ovens. And so I used to use vacuum oven all the time. And in the vacuum, this is an idea I have that I want to make something. Let's say you have delicate clothes. If you have delicate clothes, do you want to heat them up to high temperature? No. You want to dry them, but you don't want to wait for them to hang. You hang dry them. Do you want to wait that long for them to dry? No. And so you need to dry them quickly. And so this is an idea I've had. I haven't done anything about it. A vacuum clothes dryer. A vacuum clothes dryer, we just heat it up a little bit and have a cheap vacuum pump on there, and then it dries extremely rapidly. Well, this is what we do with chemicals too. Like when you're trying to dry crystals, you can heat them up, get them hot, they'll dry rapidly. But if you heat them up and get them hot, you run the risk of them decomposing or reacting with air or oxidizing or these types of things. And so in organic chemistry, this is very common because in organics, you're working with things that are easily oxidizable, like vitamin C. You never heat vitamin C up in air because it would just turn brown and black, basically, and it would no longer be vitamin C, just be some oxidation product of it. And so if you have some wet vitamin C that you want to dry, and then you put it in the vacuum oven, you heat it up just gently, not to the point where it decomposes, and then you turn on the vacuum, and then it dries rapidly. Probably, I'm sure other people have thought about this with a clothes dryer, but this is just maybe one application, something like that. So it's a combination. That combination, we look at, delta G. What's that? The sun? What if it's raining outside? It's raining outside, you have a 2-week storm. How are you going to dry your clothes? You're going to hang it up. I mean, there are different reasons. When I was drying stuff, I needed it, I don't want to wait. I need those crystals now. And otherwise, I don't want to wait till tomorrow. I don't want to wait till next week for them to dry.
We waited a long time for.
Well, I'll tell you, crystal drawing.
That took us like 3 weeks, 4 weeks almost.
But you got some decent crystals, right? Or, or 3 or 4 weeks is nothing. I spent, in crystal drawing, some crystals are so easy to grow, like sugar crystals. People grow those sugar crystals, they grow huge. In fact, there's a huge sugar crystal in our display case there. It's about this big, just one single crystal. So easy to grow. Other crystals are so hard to grow. And it could just be one thing is slightly off. And so I spent I don't know, maybe about a year trying to grow a 1 millimeter size crystal. I could grow smaller crystals than 1 millimeter, but I couldn't get a crystal bigger than 1 millimeter. I needed a crystal bigger than 1 millimeter because that's the minimum size you need to put it on an X-ray diffractometer, which is this gigantic X-ray machine, to take pictures of the atoms, basically, where their positions are in three-dimensional space. I should show you that.
What crystal was that?
What's that?
What crystal was that?
That was, the papers up here. It's called single crystal structure. Single crystal structure. Trisphenol. Phosphine oxide. The names are all screwed up because of just the phosphine sulfide. Maybe it was sulfide or the oxide. I can't remember. Or I did both, I think. No, it was ortho. Trisphenol. Well, I'll show it to you next time. Yeah. Phosphine, triphenol.
Did you ever get it?
Yeah, I got it. Yeah, it took a long time, but I got it. I started reading books about crystal growing because I wasn't able to grow the crystals. You know, the 1 millimeter size crystal you think would be easy to grow, but I wasn't able. But you know, I wasn't the first person to try this. Um, the other person, so it was like a multi-year kind of thing because the other person wasn't able to get any crystals when they tried it.
Was it like one or two things you did, or did you just like have to do a bunch of things differently?
No, I tried a bunch of things. Here it is. Trisphenylthiophosphine sulfide. This is just one of the crystals. This is the crystal here. I mean, this is the structure of the molecule here. And then the crystal is just a whole bunch of these molecules packed together.
And so you were able to determine that.
Yeah.
Why?
And so this is the paper. Is this the paper? First page of the article you requested. Yeah. This is when I was at UCSB. But I was able to grow 4. So I got 4. These are easy publications to get because everybody's interested in single crystal structures because they give you data. And so if you can grow a crystal and nobody's ever taken an X-ray diffraction, you're guaranteed publication. So I got 4 publications like this because of just being able to grow a crystal, and nobody's ever done it before. And so, and then you get the structure and you do that. Yeah. This is a very specialized paper, so they just want, you know, the main data here. And it's called the unit cell data, and they want the bond distances, bond angles, that kind of stuff.
That would be given by that machine, pretty much, right?
Yeah, right. So you put it into this gigantic machine, which is called a X-ray diffractometer. The machine I used didn't have a shield like that. The machine I used, these are not. There's 2 types of. This is called powder. Powder is very easy. You can do that very quickly, and you can get a structure for that. So these are all powder diffractometers. And powder diffractometers is a quick, easy way to analyze the composition of solids. And so if we had a powder diffractometer, we could tell if we formed the potassium, you know, trioxalato chromate in minutes, you know, and then we could determine its purity and a bunch of other stuff. So this is X-ray powder diffractometers are used to characterize solids.
Professor, this was the first time anyone crystallized the structure. How did you confirm that what you got was what you thought you were going for?
You do 2 things. One, well, we have the single crystal structure. So with single crystal structure, you can see what the atoms are basically. But how do you prove what you have is what you have? And the other way is you do chemical analysis. The type of chemical analysis that I did mostly was elemental analysis. Elemental analysis you need specialized equipment for. So what you do is you send out a sample out to people who have specialized equipment. And the samples I sent out were to here in Gardena. There's a lab that specializes in this. And then you ask them to analyze for like phosphorus, sulfur, carbon, and then you bring it back, and then you can see. That's one way. There are other ways you can do that. And I wasn't the first person to make this stuff. The first person to make this stuff, they had already characterized it, like with melting point, characterize it, melting point, crystal shape, color, these kinds of things. So you look, do I have similar crystals to that or not? I was for this publication was just because I was able to get a single crystal structure out of that. That is, take a picture of the atoms in three-dimensional space using X-rays, and then pinpoint those atoms with that. And then use a machine that looks like this. This is it. This is a single crystal X-ray diffractometer. And so in the center of that hoop there is a 1 millimeter size crystal. All I did was I got epoxy glue, and there's a little glass needle or rod, and then you just glue the crystal on the tip of the rod. That's it, and then you put it on there, and then you take pictures. People do this. Other people in the group, in our collaborative group, a lot of these people, we had one person who worked at Amgen, which is a pharmaceutical company, and they're trying to get single crystal structures of some of their drugs, that kind of stuff. So they spent a lot of time trying to grow crystals of this. It's not so easy. There's a holy grail of crystals. You know what the holy grail of crystals are? There's a holy grail of crystals where if you can grow a crystal that shows a certain type of symmetry, and that type of symmetry interacts with X-rays in a certain way, that what you can do is you can make a lens, that focuses X-rays. We have lenses that focus visible light in our eyes, right? And lenses on our cameras, but that's visible light. But for X-rays, there's no lens that can focus. Otherwise, when we shine X-rays on a crystal like that, if we had a lens, then we could see the image of the atoms in three-dimensional space like that. As it stands, what we have is diffraction of light off the crystals. And the diffraction of light goes all different ways. So we have to scan three-dimensional space. That's why you have two hoops there, and it's just scans. It spends a lot of time scanning the three-dimensional space to see the X-rays that are diffracted off the crystals. And then you use the computer to refocus all those diffracted beams of X-rays into an image, a three-dimensional image. And so this is what we get. And so people are looking for a crystal or substance that can focus X-rays into an image. That way, what you can do is you can just shine X-rays at it and then just look at the image using but nobody's found it quite yet. And so there was another group, each time you grow a crystal, they want to test it to see, does it show these types of properties?
Do they have like some idea of what it would consist of, or are they really just shooting?
Well, they do, but it's still, it's hard to come up with. So they're just trying to collect more and more data so that they can see. And then if by chance, it crystallizes a certain pattern, then maybe that interacts with light in that way. So growing crystals is this big thing, and if you're good at growing crystals and you hook up or partner with a person who's good at X-ray diffraction, then you can do a lot. And so this is what it looks like. You have that tiny crystal there. And you only need 1 millimeter, so it's really tiny, but not easy to do at all. Most people get powder, powder, and the crystals are so small you have to look at a microscope to see it. Anyway, let me just finish with this one here. We were talking about, delta G will change both. Will manipulate the temperature and RT, Ln, and Q. And so it's a combination. So like the drying oven here, would be a combination. So we would increase the temperature and do it under non-standard conditions. And so maybe we won't have as high a vacuum or whatever else. Now, when we do it under non-standard conditions, we have to be careful with this because this delta G is under standard conditions here, but it's at some other temperature. So here we would solve for the temperature here. So a typical calculation here would be, let's say I didn't want to go all the way to 0.03 atmospheres. Let's say this vacuum, what is this vacuum here? This vacuum is very weak. This vacuum, let's say this vacuum is about a half an atmosphere. If this vacuum is about a half an atmosphere, if I hook up a vacuum tube and then use this vacuum, at what temperature would the water boil? And so here, rather than, putting in 1 atmosphere, which would be standard, or 1 bar, we'll put in half a bar here for the Q, and then figure out to what temperature that is. Okay, since I don't know what the temperature is, I have to use this, delta G is equal to delta H minus T delta S, and then solve for T. We did that, but in this case, we'll just put in half a bar. Instead.
When can we substitute Q for K?
We would do that.
Or can we just do it all?
We basically do it all the time. Here, because what we want to happen here is we want it to go from non-spontaneous to spontaneous. Or we might want it to go spontaneous to non-spontaneous. But whatever it is, it's going to transition through 0. So whenever we set delta G equal to 0, then we would set Q to K. And so if I did partial reaction, let's say I only wanted 80% reaction, then I know if I want only 80% reaction, then I know at equilibrium what I need to have 80% reaction. And I call that K. This is the K, my target K, because this is where I want the reaction to stop. The reaction is going to stop once everything hits equilibrium. And so I can manipulate K, that is, I can ask for a specific K. Let's say, going back to this, I don't have to use the K that's given. Let's say I started off with 1 bar and 1 bar and 1 bar, and I want 80% reaction here. That means I'm going to lose minus 0.8, which actually that's not my limiting reagent. My limiting reagent would be hydrogen, so I'm going to lose 80% of my limiting reagent, which would be minus 0.8 bar. And that would be minus 0.8 thirds bar. And this is where I want the reaction to stop. I want it to stop when I have 20% hydrogen left, which is my limiting reagent, so I'm going to be left with 0.2 bar. And this is going to be 1 minus 8 thirds of a bar, 0.8 thirds of a bar, and this would be plus whatever it is. 2/3 of whatever this is. And so then I add these up, and this is the K I want because this is where I want it to stop. I want it to stop at 80%. And so I'm going to have this as my K value, and then I just solve this. Under what conditions will I have this K here in terms of temperature? Does that make sense?
So could we not just, like the same if we were given K, the K value, could we not just multiply that K value by 0.80, or is that?
That's incorrect. That wouldn't work, yeah. We have to figure out what the new K value is and then solve for the, in this case, we can solve for the temperature, which that new K value would be. Were there any questions on chapter 18 stuff for the test? Well, you can ask me tomorrow at the beginning of the class too.
But I want to give you back this quiz.
Can you show us how you do it about the quiz problems?
How to solve the quiz problems, these quiz problems here. Okay.
Well, I think some people just solve it the exact way I would probably solve it. Yeah. So we want to know how many milliliters it takes to dissolve a certain amount. And so in order to figure out
How much dissolves is solubility. We don't always look for solubility. If we're doing fractional precipitation, one of the biggest mistakes is that people calculate solubility. You don't calculate solubility for fractional precipitations. You calculate the concentration required to precipitate. And so the solubility of water is your standard, 0, 0. We just see how much dissolves. In that case, it's plus S, so we get S molar and S molar. And so here KSP is equal to S squared, and S is equal to the square root of KSP. Now, a lot of problems, they just have you stop here because, we're just interested, what is the solubility? So this would be the molar solubility. How many moles would dissolve in a liter? But, oftentimes more complicated questions, they just ask you to do an extra step. The extra step is how we use that solubility. So if we know already how many moles will dissolve in a liter, let's say, we have 1 mole dissolves in a liter. So what if you had 2 moles? Then you need twice as much. You need 2 liters. And so, well, how much did we have? We had 250 milligrams. So the way I would do it is I have 250 milligrams of silver chloride, and then I'll just convert it to grams. And then I have grams of silver chloride, and I gave you the molar mass of silver chloride. It was 143.32 grams per mole. Okay. And then I figure out how many moles of silver chloride I have. Well, I don't have that many moles of silver chloride, but the solubility is so low. What was the solubility? The solubility was extremely low. And so the solubility was 1.3416, it looks like. So 1 liter only dissolves 1.3416 times 10 to the minus 6 moles, or micromole. And so if I only dissolve a micromole in a liter, well, how many micromoles do I have? I don't have to calculate how many micromoles. I could just use conventional analysis. And so this is what I was thinking. You don't have to get it in terms of grams per liter or milligrams. So just use the solubility as is, and then just convert everything else to get that. And then we have 1,000 milliliters in a liter, and then there's 20 drops per milliliter. And so I would have just done it using conventional analysis like this, putting the solubility in here, and then get the 1.6 million or whatever drops it is. The other problem is the same, except the solubility is different. And so what we do is we get the combined equation. And so I'll just go straight to the combined equation since I wrote it up earlier. This is the KSPF equation. The KSPF is like 0.02 something. So versus 10 to the minus 10. And so already we can see it's going to be a lot more soluble here. And then for the ammonia, what was ammonia? 6 molar, 6.00 molar. Yeah. This is 0 and 0. Now, one of the tricky things is, how they phrase the question. Is this 6 molar at initial, or is this 6 molar at equilibrium? Oh, initial. Yeah. And so then it would be minus 2s plus s plus s. Yeah. And then 6.00 minus 2s, and s, and then s. And so
Once I get the solubility, then we do the same thing. The solubility is going to be a lot higher here. K is a lot bigger. But still, the 6-line assumption, I mean, may not work. Did it work? Do we even need it? Actually, we don't even need it, because we just take the square root of both sides, right? Is that what you guys did? Yeah. Yeah, because KSP is going to equal S squared over 6.00 minus 2S squared. And so we don't have to do much math in this particular case if we take the square root of both sides. And then we solve for S. Once we solve for S, then it's exactly the same problem, except the solubility is different. The solubility is higher in this case. So we eliminate this one and put in the higher solubility here.
So what was the solubility that people calculated for this one?
0.29.
What was that? Or do you remember?
0.29.
0.29, yeah. 0.29078 or something.
0.29078 moles. So rather than having micromole amounts, now we have tenths of a mole that dissolve. And so the solubility is a lot greater. And therefore, the drops come out a lot smaller, 120 drops. And so it's the complicated thing was normally we stop at solubility, but this is just asking one extra step. The one extra step is, using that solubility to figure out how much dissolve that's it. Uh-huh. Yeah.
Of the concentration of NH3, did you need to plug the value that you got for S into the equation for NH3 in order to get the concentration of NH3?
Well, the concentration's fixed for the NH3. So it's fixed here, but we need to know the initial amount here that we're going to use for this. And so there's another way you could do this, where you could figure out, this is different because the thing that makes this problem easier is that there's no solution dilution. We're just dumping the NH3 to a solid. If we had to do solution dilution, then I would be doing like Z, this many milliliters plus Z milliliters of NH3. And so since I can skip the solution dilution step, I wouldn't be doing anything beyond this, except whatever mole. So you're saying once we get this, and we figure out how many moles of NH3 we have, and then from moles of NH3, we figure out how much. But the problem is once we get this and we figure out the moles of NH3, then we do the moles of free NH3. There's two types of NH3 present. There's free NH3 and complex NH3. And that free and complex NH3 is going to be the total NH3 we add in there. And so you could do it like that, but it's a long way of doing it.
So how would you do it with asking us to, the way it was asking us for NH3 versus, if you did it with silver chloride?
Well, this is this, okay, I see what you're saying is the solubility.
So like a lot of us got S, and then we're like, cool, now what?
Okay.
So I think it's that last part that we're actually struggling with, to go from using the solubility of HUCl to finding how much ammonia we needed to use.
Yeah, because it seems that like this point, we haven't even taken into consideration ammonia in this equation, really.
I see what you're saying. So you're saying that because the ammonia, how is this solubility connected with the 6 molar ammonia? Basically, you're trying to figure out like the moles of ammonia you need to get the liters of ammonia present. But in that case, you don't have to do it that way because when we're doing the solubility, this is actually the solubility in 6 molar ammonia because we aren't doing this solution dilution. If we were, then I see what you're saying. You're saying that you're trying to figure out based on the moles. Okay. But what I'm saying is that this comes from the total silver chloride that dissolved here, and this would be the required volume from that.
So it would really, so it would be 0.2907 moles of silver chloride in 1 liter of ammonia.
Right.
And that's where we would change from the values of ammonia to having it be like 120 drops of ammonia. That's the.
Yeah. This would, well, I don't know, I understand what you're saying for the connection, but this is actually the silver chloride that was originally present here.
Mm-hmm.
And so what we need to do is we need to figure out how many of this gets into this.
Mm-hmm.
Let me see if I can have a better way of explaining it because,
Explain it that would be helpful.
yeah, because I know what you're talking about. I've done it. I could do it the other way too, which I've done. I'll show it to you, but I think we're out of time. So.
So the main difference between question 1 and question 2, even though we're dealing with water and ammonia, which is very different, it's just finding different S's and then you still plug it into the same equation, it seems like.
Right, for the solubility, you would do that. But I see what the confusing part is. This is the solubility you're thinking in water, but in reality, this is the solubility in ammonia. And so I understand what you're thinking. What you're thinking is very good because you're thinking about, how does that relate to the ammonia, versus if this is just plain
Yeah, because I
water.
saw you writing like it says silver chloride, and I'm like, okay, but that looks like 120 drops of silver chloride. Right. The
No,
way the conversion
no,
is written.
this would be liters of solution here.
So it's 120 drops of solution, and in this case, the solution is
This is ammonia, right. And so this is the solution
So the
that we're
first one
adding
was, the
here.
solution was water, and the second one solution was.
Ammonia.
Okay, so
Ammonia.
that's how the conversion.
Right.
Yeah, I was like,
Okay, then that makes sense, what you guys are saying there.
Yeah, that's why, and I've also never seen it, I didn't know we could use it as a conversion factor like that, it makes sense, but
Okay.
I just haven't seen it, so.
Okay, but I've done it a different way, so I'll show you.
Yeah, thank you.
I'll just submit this. Quick question. So the question asked, we need to calculate the number of drops. So how did you get 20 drops in the?
This is the approximation. There's roughly 20 drops in a milliliter.
Okay, so you just.
Yeah, this is just something that's known for solution.
So this would be a wrong answer if I didn't add that.
No, you need to add that.
Okay, on both of them?
Yeah, both of them.
No. For the homework, chapter 18,
Mhm.
the question you did on the videos were different numbers as compared to.
Yeah, did you already do the homework from the other one?
Yeah, I did the problems you did on the Zoom, but the other problems on the assignment,
Uh-huh.
are we supposed to do all of them? Or the ones you did on the video?
No, you could just do the ones I did.